All right. I don't think that was the world's smoothest transition, but it's a start. Sorry for the late start there, boys and girls. It turns out I have successfully kinked my cord to the camera here. So if the camera just goes out in the middle of the stream, I'm not gonna try and fix it. We'll just roll with the camera going out as is. Hopefully it doesn't happen. So, for those that have not caught this stream before, this is a stream for Pwn College. Pwn College is a website that is free and open to anyone. You can go to it right now on the internet. It's right here, just pwn.college. As the homepage here says, it is a site where you can learn how to hack. This site consists of a series of dojos or content that you can kind of go through and learn about cybersecurity concepts. It is structured kind of like a martial arts dojo here. There are some instructions as far as how to get started. This stream in particular, if we click up here on dojos, is following this software exploitation topic. Specifically, it's following a course out of Arizona State University, CSE598. We click here. The thing that we're currently discussing are format string exploits. And we can explore this topic. You'll find pre-recorded lecture videos as well as slides. You'll find recordings of streams and live discussions as well. When you are ready to try and tackle content, you can launch a challenge right here by clicking Start or Practice. We should get a little box here that says the challenge started up. Once you have that, you can interact with the content via this workspace or desktop icon. Click the tab up here. We have a VS Code-like interface where we can do some work. If you prefer a more graphical interface here, you do get a live VNC interface right here in your desktop or in your browser. And if you are like me, you may prefer, oh no, it'll be okay. You may prefer SSH, which you can also do. The setup instructions are on the home page. SSH hacker at dojo.pwn.college. And assuming that you have configured yourself correctly, this will drop you into an interface where you can work on these challenges. This particular stream is an office hours stream. So that means it is geared to be a kind of question and answer format based upon what students are struggling with or things that they are not necessarily sure about working through the content. So the general format is people on Twitch ask a question. I do my best to answer it on the fly, and we see what happens. Sometimes we discover some great things. Other times I fail to demonstrate something and it becomes an utter mess. In either case, it's sometimes entertaining. And so with that, I would leave this. Yes, Twitch says live demos are always a fun time. I think the live component is important, right? You get to see me make a mistake. Like, I am not infallible by any means. When I say read the man page or check this, try stuff, that is literally how I remember these concepts, even though I may have been exposed to them in the past. Right? Now, I don't see any questions here in Twitch at the moment, which is fine because there was something that I wanted to discuss anyways. And that was what I utterly failed to discuss in the 7 minutes that I had at the end of class. Not specific to format strings, but level 7 here discusses something that is not specific to format strings, but is definitely relevant to these challenges here. Our kind of description for this challenge is use a format string exploit to overwrite and it says GOT entry, right, or GOT. GOT is shorthand for global offset table. And the global offset table, one moment there, 7, go. Twitch says that they happen to be working on 7, but they don't think they have any conceptual questions about it at the moment. Yeah. So one of the things, I don't have the slide handy, but from class, one of the consistent themes over like the first half of this semester is we look at a particular system, right? Or functionality that exists. In this case, it's printf and format strings. And the lecture slides here are set up such that this is how you leak data or how you read some arbitrary memory, right? And then there is how do you write data, or how do you overwrite something in memory with user-controlled input. And you'll find that over the first half of this semester, almost every module kind of follows this format, where we look at something and then we say, how can we turn this into an arbitrary read? Or we look at something and how can we turn this into an arbitrary write? And so once you understand how to get an arbitrary read or an arbitrary write using a system, the question kind of becomes, well, what do you want to do with it, right? Where is the value in having this arbitrary write? How do I turn that into a privilege escalation or getting control of execution? And level 7 here is, as far as I recall, the first level that requires using a very specific approach, using this global offset table. Let's see, that is not large enough. Give it a moment for the old Twitch delay. I'm blind, so we'll accommodate me here. Now, for these particular challenges, one thing that you can do... Oh, I'm blanking. I want to say export PS1. No. There is a environment variable that I don't remember off the top of my head, where you can shorten that prompt. Environment variable prompt. PS1 is a Windows suffix. You know it's it is PS1. There we go. It's also the Windows suffix. But you can customize your prompt here, because some of these challenges right now have really long host names. And so this will allow me to kind of crush this over here to the left-hand side. Random factoid. So, what I was trying to do, see if I remember where I put my example. I think it was here. What I was trying to do is something like this. I was trying to compile a binary in class, and I was claiming that there was this railroad thing, right? And I didn't verify that what I was doing was going to work, which is where the craziness happened. When I was using my compiler flags, I was passing this -WL-Z railroad. And what this should do, if you look at just this part that's highlighted in yellow, is this should make the railroad protection mechanism, which railroad stands for, let's see if I remember this right, relocation read-only, right? That's what the rel is, the relocation table, and then RO is for read-only. And so this railroad protection mechanism, which it makes a special region of memory read-only, I wanted to force the compiler to make this partial. Because if nowadays, if you just run it normally, you see here that the security mechanism is full railroad. And for what we're going to discuss and to exploit this vector, this property of ELF binaries, we need to not have full railroad. Now, there's two other things that you could see there instead of full railroad. The first is what we just saw up there, partial railroad. Which is what you should see on most of the challenges. And then the other thing that you can see, you may see there, is WL-Z, no rel row. No rel row. Now, all of these settings, whether it says no, partial, or full, what we're referring to is this global offset table, this GOT thing that is referenced in the description. And to understand what the GOT is, we have to look at a binary and kind of run through it. So let's first show the binary that we're working with here. So this is a pretty simple binary. We have a main function somewhere here. If we provide it with an argument, then it's going to call this arbitrary right function. Arbitrary right does exactly as the name kind of indicates here. It asks for a location. It then asks for, here it asks for a location. It then reads in a pointer. It asks for a value, and then it will assign that value to that pointer. Somebody asks, is CS worth it? CS is a very demanding field, and if you enjoy it and you enjoy working on hard problems, then it is a fun thing to pursue. Just know that it's a lot of work. And it's not, it doesn't stop after like college. You're just forever learning new stuff as the field progresses. So with this arbitrary right function, we'll take in a location and a value, and it will put the value at the location. And that will occur if we provide an argument. Then it will say, first call to printf, second call to printf, and it will exit. We happen to have this win function here that will open the flag, and then you send file to output it to stand it out, but you'll see that it's not called here at all. And so that is the entire functionality of this program, and we will run through this several times to kind of understand these mitigations. So first off, we are no rel row whatsoever. And if I start this, if we have GEF or Jeff installed in GDB, there's a command GOT that we can run. This shows us the values of the GOT, right, of the global offset table. Good old Jeff. I mentioned in class, like, oh, isn't there a PLT thing? And I got a pwn.debug. Their command that does something similar to this is PLT. And there are two different parts involved in what I'm about to describe. There's the GOT, the global offset table, which is what we see right here, and the procedure linkage table, which is involved but is not this. Typically, the two work together, and their purpose is to resolve dynamically linked symbols. Now, I apologize. I'm going to have to throw up the streaming window real quick. I'll be right back. Okay, I apologize for that, everybody. Somebody was approaching my door, one of my neighbors, and I didn't want the dogs to go off and make a big ruckus, and so I jumped the gun there to try and prevent quite the ruckus. So we were talking about RELRO and the global offset table and what the purpose of this is. Well, recall that when we compile a binary, there are dynamic libraries that are linked to our ELF, right? And so this a.out file, it relies on libc, and we don't compile libc into every binary. Instead, there is just a shared library, which happens to be located here, that contains libc. And so when our userland binary here, a.elf, needs to call a libc function like printf, it will call the printf function that is inside libc. But if binaries are PIE, then this is dynamic. And the address of libc will change, or not PIE, due to ASLR, the address of libc will change on every run. So right here we have 7FFF, 7DF is the beginning of libc. And then if we run this again, we now have F68, or no, 7DF. And what was it before? 7DF. That is GDB, making things nice for us. But the address would randomize due to ASLR. Is that right? No. 7DF and 7DF. So if I were to run it, what would I need to do? I would need more than one window. You can run it down here. Take that out. Oh, but then it wouldn't pause because it doesn't read anything. Wait, I can give it an argument that blocks PSAUX grep a.out, and I cat proc 2390 maps. That has libc now at 29EA. And then if we were to do it one more time, two, 4, 6, 3, it is now at 6CAA. So normally the address here for dynamic or shared libraries are going to change due to ASLR. One of the questions from Twist Chat here is the PLT should only get called once at the first call, right? The answer is yes, and we're going to run through that. I just wanted to prove that the address does change first, so we have some idea of why this exists Okay, so this here is going to call printf, and if I break at that point, break star main plus 50, and we continue, we're about to call printf. And we see that where execution is going to go is printf at PLT. And if we look at the GOT entry for printf, it is not that address, right? And that's because we will always be jumping into the PLT. We step inside, and right here, inside the PLT, we see this address getting loaded into or being a jump target. So we are jumping to the address that is at this right here, which is the GOT for printf. Printf right here. So at the address 403408 is where the procedure linkage table will jump. And it's getting that from the GOT. And we can show that as well. We see that at this address is this value. And so this value will decide where we jump to from this point. Now, the question would be, well, what is this point? And what we'll see is that this goes, no, not address, this goes to a point where it's going to just push an index and then jump to a common point. And right below that, what do we have? We push a different number and then we jump to a common point. This is inside the PLT when we're deciding what it is that we need to link. Twitch says, can I think of PLT of libc function as the address resolver for the libc function? Kind of. So if we keep stepping through here, like ultimately that's what happens, right? But the PLT is inside the main binary. And so if we jump to this first point, now what we're going to do is we're going to push 2, and 2 is just a magic number here that will be used in the resolution process. So then we jump to this point up here, and this point is actually directly above where we were. If I look at like 20 instructions where I am, here is that point that we jumped to initially, right? We land right here, we push 2, then we jump to the top of this region. Here, what's going to happen is we're going to push an address or a location that is needed by the dynamic loader. And once we jump from there, we are suddenly in this DL runtime resolve. Well, where is this? This is inside the loader, and we can show that right here. We are inside LD. If you are not familiar, LD is the dynamic loader. So like when you start an ELF, the very first thing that runs is actually LD. That is what kind of pulls everything into memory and starts replacing symbols so that dynamic libraries work. Somebody says, I love DL runtime resolve, a very useful function. Yeah. We're not going to go down the rabbit hole that is there. We're going to end the discussion as far as, well, how does this work, is that we jump into the dynamic loader and its function is going to be to find printf inside of libc, and then it will return. So if we finish from here, we should return from the dynamic loader, and all of a sudden we're back inside of main. And we're on the other side of that call to printf. If we take a look at the GOT, printf, Jeff is nice enough here to color it green. I don't know if you can see it on the stream here, but printf is green where the rest of these are yellow. And we see that that address has changed. And so now we have the beginning of printf stored in that GOT entry. Now, if we step a couple more instructions, we're going to call printf a second time. And when we do that, you'll see we step into the PLT again. Except now, when we jump to the address that is stored at this location, this is now the beginning of printf. Oop, I'm sorry. Examine the address at that location, and we see that that is printf, and we would see the first instruction there is the NBR64. And so that means the second time that we go into printf at PLT, it's not going to have to go through that dynamic resolution process, right? But where are we right now, right? Because we are still at printf in PLT. The PLT is inside your main binary, right? The thing that you're starting up. It's important to be aware of this, right? The end result, as Twitch pointed out, is this is how we dynamically figure out where symbols are. And so it's kind of like this lazy loading process. Now, with no rel-row, what rel-row does is it prevents you. Question: what happens if you try to leak print at GOT before it's loaded? So much like we have like open right here. Open has not been called. If we look at all of main, right? Open hasn't been called. Now, if we were to leak what is at the GOT entry for main, we would see this address here. So let's examine the address right. What did I get wrong there? Oh, I picked the wrong thing right here. Examine the address of the GOT entry, and we see that we get open at GOT PLT. And so this doesn't point to, and then if we were to take that and examine, say, 20 instructions at that location, that is where we grab this. Where am I? 4080. That is where we go right here. We push the magic number, and then we jump to the top of the PLT, right? And so if something isn't loaded, when something isn't loaded, we will jump. Which one? What number was this? 4. We'll jump to some point in here. Let's give me 30 instructions so we can see the whole thing. We'll jump to like here or here or here or here. We'll jump to one of these little sections where we push an index and then we jump to the top. And so that is what will be there if it hasn't been resolved yet. Because what's happening with the GOT is it's like lazy loading these addresses. And so these right here, like 401060 is this right here, where we push 3 and then we jump to the top. 401070, well, that is right here. We push 4 and then we jump to the top. The top being right here. And so if it hasn't been resolved, then it's going to default to an entry like this to get it resolved. Now, what rel-row does is it protects these memory addresses. Yeah, it is confusing, right? Because it doesn't make sense at face value why we have to push 2 or why we have to push 3, right? It's just an implementation detail. And so like if we look at 4070, that's this right here, which is pushing 4, 0, 1, 2, 3, 4, right? And so it's pushing an index to itself, to like its own entry. Because what this number is being used for is this number then gets read in by the dynamic linker, and that's how it knows which entry to update. So it's basically a jump table. I don't know that I call it a jump table. I don't know that it's not. Because like a jump table is like this is just a list of addresses. Like this itself is not a jump table. It's just an array of 64-bit addresses. Right, where like a jump table is where you would compute where you're jumping to dynamically, and that's not happening in either of these. I mean, there's like a dynamic jump location, but we aren't dynamically computing it based off of some value, right? Some value that changes. So I'm claiming RelRel protects these values. So no RelRel means that these values can get overwritten. And that's not particularly interesting, right? What is a bit more interesting is partial RelRel. Now, you'll notice that I have no PIE. This is a compiler-enforced phenomenon as of a recent version of GCC, and it's why in class I was very confused. This changed like a year ago, but I had forgot that it had changed because I don't compile binaries without RelRel very often. But GCC will only let you do partial RelRel or no RelRel if PIE is also disabled. But from a can the ELF do it? Can you make an ELF that has partial RelRel and PIE? The answer is yes. You used to be able to as of like a year ago, a little bit more than a year ago. However, now GCC as a compiler, as a build tool, will not allow you to do that. But per spec, you totally can. Fun fact. Okay, so now we have partial RelRel. And if we run the binary, this is where, let me first take a quick look at my source. What do I have here? Okay. I'm going to comment out win for right now for reasons that will become apparent. Okay, so now we have, no, I don't want to do that. I want my build. Now we have a binary with partial RelRel. If I run this, and since we have no PIE, that means that the base address of the binary is constant. It just is because of PIE. And that means that if we start it and look at the GOT is going to be a constant, or the memory addresses here are going to be consistent across runs because the binary is being loaded in at the same base address, right? And the GOT is part of the binary. So because we don't have PIE, this is a constant value that we can reference. Now, what we can do with partial RelRel is if I run this with some argument here, so it asks right where, and I give it, that was unfortunate with my copy, we give it the address of printf. And I note that I'm not using GDB to set this, right? GDB will just let you do all sorts of illegal things. And so this is the program modifying itself, right? And say I want to write to there, and let's write the value leet beef. Leet beef is a good value. We see that we get a seg fault, and we seg faulted at leet beef. If we look at the backtrace here, particularly frame 1 in main, the question is, well, how did I end up at leet beef? Well, main, remember, rip points to the next instruction. So I didn't seg fault here. I seg faulted trying to call printf at PLT. And printf at PLT, if we look at the GOT, it now points to leet beef. And so if I have the ability to arbitrarily write, and I can know where a got entry is, and it's not full rel row, which we haven't discussed yet, then you can write whatever memory address you want here. And when that function is called, control will jump to wherever you've written. So the program tried to call printf. It doesn't know where printf is. This goes to the PLT. The PLT jumps to wherever is listed right here. And so this is a way to gain control flow. In 466, we talked about ROP and overwriting the saved return address. Somebody says, partial rel row also forces the GOT to be before the BSS in memory. I don't know that to be true. I don't know it to be false. I've never considered that. Okay, so like it doesn't make sense to me, but I don't know enough to say that you're wrong. Because right here, the BSS would be down here. And so then if I compile that with no rel row, this was partial rel row. There's no rel row. Now your BSS would still be right here. Because BSS is read write. Am I horrifically wrong? Like our memory layout is the same, right? Our executable code region is, oh, you're talking about the, oh, you're saying the GOT, not the PLT. Okay, so then GOT 403, okay, yeah, versus GOT, okay. I was thinking about the PLT. Okay, so then up here we are at 404, 404 read write. Over here we're 403, which is still the read write. No. We have an additional page of readable there. See, but the GOT is still, like, I don't tend to think of else sections, and this is why, like, you could be right and I could be wrong. Or I don't know if I'm right or wrong. I'm just trying to reason about it here. I don't think about else sections. I just think about, like, regions of mapped memory. And in both cases, it's mapped in read write. Right? But I'll say, I don't know, maybe. I don't have a quick way to like dump that out and prove it right or wrong, because I don't know how to. Does Jeff? Oh, I could probably do it with Pwn Tools, because Pwn Tools will let you get BSS space. But I'm like rabbit holing here. We can look at it, but I'm not going to do it right now because I want to finish this rant about rel row. Somebody says, make a global variable on the BSS and check. I guess I could do that. That's not too much. Int my global And then just to make sure it doesn't get optimized out, let's print it right there. Okay. So partial rel row. What did I do? Oh, that's puts, not print. Okay. Partial rel row. GDB. Let's have symbols. Or yeah. GDB a dot out. We'll start it. We'll look at the GOT, and we will print. What did I call it? My global. I'm a little behind on my sleeve, so bear with me there. Print my global, except I wouldn't want, where am I? Context. Yeah, I should be able to print. Okay, and then the GOT. And so with partial rel row, it is the GOT is behind the globals. And then the claim was if I go no rel row, then yeah, in both cases, the GOT entry is behind the globals. Does Twitch agree with me based on what we saw? Like, I think I've heard of what you're referring to, but I think we just showed that that is not the case, at least currently. Because in both cases, our global value was at a greater memory address than the GOT. Because I think at one point you're right that you could overflow from a global into the GOT. All right, Twitch is claiming it doesn't have to, and I just happen to, we happen to luck out there. I don't know enough about that specific detail to like be authoritative, but I can say that that wasn't the case here. Okay, so now let's continue on our exploration here of partial rel row. So we said with no rel row, I could overwrite printf. Now, if I do this, and we build it with partial rel row, okay, we debug it. Oop, I need that GOT address. Here's printf. I'm going to try and do the exact same thing that I just did, right? And then we're going to write it to be leet beef again. What do we think's going to happen? Partial rel row, and I'm trying to overwrite this printf value. No, nobody knows, right? It's a mystery. Okay, so let's do it. Well, we blew up at leet beef again. And if we look at the GOT, we see printf, the got entry for printf, there's still leet beef. It will be overwritten. So far, partial rel row isn't doing a whole lot for us, right? Let's do it a third time here. And we will... What happens if I want to overwrite puts? Is this going to work? Now, in this case, puts is green, so puts has been resolved. Is partial railroad going to save me here? Twitch also says no. Okay. So we give it that. We give it wheat beef. That one exited normally, but that's because we don't call puts again. We'll say puts, goodbye. Build.sh, GDB a.out. We will run, or we'll run with an argument so that it gives us our arg read arg write. We get our got entry, and now we're going to overwrite puts, which has already been resolved. And we'll give it leet beef. Okay. We still seg fault again, and we seg fault on puts. If we go to backtrace, frame 1, and then get some context here, we'll see that we were calling puts. And if we look at the GOT, leet beef is the entry for puts. So the question is like, well, what good is partial railroad? Right? So far, it hasn't done anything. And from an attacker's perspective, that's kind of true. Partial railroad very rarely prevents an attacker from taking advantage of the GOT. So what I changed here now is now inside my arg write function, instead of calling puts, which is what was there, it's calling printf to display this message. And we have partial railroad. If we run in this scenario, we take a look at the GOT. Nope. I messed this up because of this. Actually, that's fine. Okay. GDB a.out. We run it with A. We look at the GOT. We see printf has resolved, scanf has resolved, puts has not. It's asking for where. Well, let's try puts. So we say, I want to write at the address of puts. Now, this write what, if we take a quick look, was output by puts. And right now we are on this scanf call. And so at the point right here where we're on scanf, puts has been called. And so if we take a look now at the GOT, we see everything has resolved. Puts has resolved, printf has resolved, and scanf has resolved. And so now if I give it a value, we seg fault. But where did we seg fault? We did not seg fault where I expected us to. Why? This put should have been... What partial railroad does is once everything has been resolved, it locks in and becomes read-only. somewhere what did not resolve? Like that should. You got that, got that, got that. Build.sh, gdb.out. We run it with an argument. We get our GOT entry. Okay, so now everything's resolved. And I should segfault on the right if I have done this correctly. What have I done wrong? I have done something horrifically wrong. Read in a pointer, that's fine. Read in a value, that's fine. We dereference it and we put it there, that's fine. But we saw first call to printf, second call to printf. Now, both of these, all of these printfs have a lame string argument there. So those are in fact printf. Like what I should segfault on is this right here. Partial railroad, no PIE. And if we a.out a OX404020 OX 1 2 3 4 5, and it is just happy as a clam. Huh. Let's finish from here. Okay. And let's go all the way up to this arbitrary right and see what happens. We got our GOT. Everything is resolved. Everything's locked in. If we print pointer, pointer is correctly that. And if we examine the giant hex, actually we can just print star long star pointer. That is the value that it says. So then when we step from here, you got to step twice, print RAX. Now we're looking at the register. That value is that right there. Then we print RDX. And that is that value. Right here is where I would expect a segfault, but we don't see it, which is interesting. So that is a fun one. Aren't I writing before the call, though? So if they've resolved, then it's been called, right? And if we go up here and we look, this has been resolved. Goodbye, sir. So that's interesting, but that's what partial railroad does, is once everything has been resolved, it locks the GOT. As far as why that isn't happening right now, I'm not entirely sure. I'm going to blame some strange compiler thing. Now, the last thing to look at on the topic of railroad and the GOT is full railroad. Yeah, Twitch is saying, did I write scanf after scanf was called? And the answer is yeah. The scanf was called here, scanf was called here, and then I'm overwriting it right here. And so I would expect that to seg fault on the right if partial rel row was working. It's a mystery. But full rel row does work, hopefully. If we just compile this normally, then we should have a happy binary that has full rel row. Now, full rel row is different than both of them. So the functionality of full rel row is we're going to the loader is going to resolve every one of these before we even get into main in our binary. And so this now has full rel row. It could be like a, well, no, because I did it with without GDB. I was like, maybe GDB's doing something. I don't know why that partial didn't work, but full rel row. We got this. We start. If we look at the GOT, everything has been resolved. We get our arbitrary write. We say we want to write here. I want to write this. And we seg fault, as you would expect. This is what I expected to see in partial rel row, but we definitely see it with full rel row. We seg fault, and the location that we seg fault is when we are trying to write to RAX. We're trying to move RDX into RAX. And if we look here, RDX is my value, and RAX is this address, which is where printf is, where the printf entry is for the GOT. The only thing that I changed, I actually ran through these. The only thing that's different from when I did this earlier was that right there was the debug symbols flag. And so give me one of these entrants. Cool. This and this. Oh, that is a silly way of doing that because it's not obvious that I overwrote it. OX1337, 1337. And that is jumping. And there's only 2 entries there with partial railroad. What was my address? I wouldn't expect that to be the case. Four zero 404018. Right, we seg faulted, but where did we seg fault? That is seg faulting at the jump from main and not at the overwrite. That's interesting. I'll have to figure out why that is happening because partial rel makes the GOT become read-only after everything's been resolved. That's what partial rel does. And the reason that partial rel doesn't matter, generally speaking, is because it is unlikely that everything is resolved. Like most of the time in a sufficiently large program, there are dynamic symbols that have not been resolved, which means partial rel-row provides no protection. But by default nowadays, everything has full rel-row. And so that is a vector that we can use to change control flow of the program. Question, isn't full rel-row slow? Is it really default nowadays? Yes. So if we, there, I don't have an a.out. We gcc do.c. I'm not providing any hints to the compiler. It gives me a couple warnings because warnings are a suggestion. We see full rel-row, canary, NX, and PIE. So by default, full rel-row would be enabled. And you are correct that for like a large program, it would be, I'm not going to say slow in the sense of noticeably slow for a user, but like on a sufficiently large program, there is overhead to resolving all of those symbols at start. But that is the default. So how can we use this to, is it new as default? I want to say that was around a year ago, the same time that they made it so that you have to disable PIE to do partial rel-row. Like a year ago, partial rel-row, I want to say partial rel-row was default. A little bit more than a year ago. And so a little bit more than a year ago is when that change happened. With GCC. I don't know what other compilers do. So if we build .sh and then checksec a.out, I have this binary now that has partial rel-row. How can we take advantage of that? If we look for our win function, because PIE is disabled, this is a constant value. And this printf guy here is a constant value. And what this means is I can say I want printf, I want to overwrite the got entry for printf, because I know printf is called later in this. And I want to overwrite it with the address of win. And when I do that, it does nothing because I'm using GDB on a setUID binary, which is going to drop privileges. So let's do that, but not have GDB. Right, what? There. Right where? Overwrite the got table entry for printf. Write what? Write the address of printf. What have I done? Oh, I'm in the home directory. Home directory on the dojo is no suid. I wonder if that CP or demo is what broke me here. Demo to temp demo a.out with an argument, address of the GOT or GOT entry, address of win. Since I copied it, it's no longer suid. Sudo chown root a.out sudo chmod u plus s a.out. The little things. There we go. We've got a flag, right? And so this is what would normally happen. The rest of it was all me not thinking about details of the dojo there. And so what we did is we overwrote the GOT entry. Question, can I talk about level 9, which has no loop for us to do multiple printf? So as a general rule, I won't talk about specific challenges because we are avoiding that as a whole. I will talk about that scenario. Like we have that scenario right here, technically. And so I was able to overwrite the GOT entry for printf. So then when the binary called printf next, it would actually jump to my win function. Now, the question that was just asked was, what happens if you only have one printf, right? Well, one printf, what you functionally have with printf is arbitrary read and arbitrary write. Right? Now you can't necessarily like use a read to perform a write, but you can leverage printf using like %LLX or number $LLX or number $N for write and LLX for read, right? And so having one call of printf is functionally the same as having this arbitrary write. Somebody, does full railroad mark GOT read only after everything has been resolved? So it has to be after everything is resolved, if you think about it, because when the loader starts up, we don't know, is this, let's compile this full railroad. Okay. So this has full railroad, right? If I run this guy over here, PSAUX, grep a.out, I really should just do cat. If I were a clever man, proc pgrep a.out maps. And then let's grep libc. Cool. And then let's take head N1. There we go. So that's the beginning of libc, right? For this run, it's 456000. And this is only true for this run. And the loader doesn't know what it's going to be if I start it up a second time here. And so we do this a second time, and we say, all right, hey, what's going on? Well, now it's 215000. And so the only way to resolve the dynamic addresses is to have it be read-write. And then when the loader first starts up, and we are just looking at, or the loader sees all of this right down here, it will resolve all of the symbols before control flow goes to main inside of a.out. And so from the perspective of the userland program, if we start, so we're at the beginning of main, before main, oh, that's partial railroad. Gosh dang it. That's because I'm in a different directory. Check sec. A.out. Where am I? Demo. Check sec. A.out. Okay, full railroad. GDB. A.out. We start, so we're at the beginning of main. So before main even starts, all of these have been resolved. And if we look at where the GOT is, we see that that page of memory is read only. And that is, we're at main plus 0. I believe, and we can find out real quick here, we can do start I, which starts you at start, right? It sets a breakpoint at the first instruction of the executable. Right here, we see it hasn't been resolved. But that's because we haven't gone from start to resolving symbols to libc start main to main. Right? And so it isn't known until it's loaded in, right? So at start I, we're at like literally the first instruction that is in, we're at the symbol underscore start inside the elf, right? And so when we look at what's going on in memory right here, we see that there is no libc. And so since libc doesn't exist yet in this virtual address space, how could we know where all of this stuff is? But between underscore start and main, right, all of that kind of setup that the loader does, set a breakpoint at main, and then we continue on through, all of a sudden, now everything's resolved. And that makes sense because like it isn't known at the very, very beginning because libc hasn't been mapped into memory. And so what full railroad does is it says, hey, every symbol that we have, we're going to map it in, and we're going to resolve all of these symbols. And we're going to do that before the first instruction of main. So from the user land process's perspective, it is always read-only and already resolved. That was a good question. Okay. Hopefully that's pretty clear. One cool thing about the GOT and pwn tools is if I go from pwn import star, I believe we use this a little bit in 466, but if you haven't seen it, there is a elf command that pwn tools exposes. And so I can say E equals elf. And what is E now? E is this elf representation of the binary. Somebody is asking, I'm trying to confirm something I'm seeing. Does writing with %n change the count for n? For example, if I wrote 1 byte, does it increment by 1? I believe that is the case. We could, if you write, no, because what the counter for %n is the number of bytes displayed up until that point. And %n doesn't display any bytes. %n writes to a memory address. But the number of bytes that have been displayed to standard out from just %n is 0. Give it a moment for the Twitch delay. Because what %n is isn't displayed a little misleading though. Oh, now we're hitting hitting something crazy here. Like we can throw together an example after I rant about this, then 9, then we can delve into the deeper workings of %n. No, like I'm cool looking at it here. Like we'll figure it out together. But my understanding, based upon the man page, right? If we man3 print f and we say %n, actually it's going to not say percent. It's just going to be n. Man3 n. Show me n. The number of characters written so far is stored into the integer pointed to by the corresponding argument. That argument shall be an int star or variant whose size matches the optionally supplied integer length. No argument is converted. The specifier is not supported. Yeah. This behavior is undefined if the conversion includes any flags, field width, or precision. And so writing... So I guess you would have to say, well, what do they mean by written so far? All right. You know, you could make an argument that it's unclear there. You technically write to a location. Technically, you don't, because write itself has a very specific meaning, which is why I say goofy things like write from memory and read to memory. If you print the value OXFF, is it considered displayed? So that would depend on how you are displaying OXFF, right? Are you saying that you are printing the byte FF? If that's the case, then that's 1 byte. Now, if you are saying I'm displaying the characters 0xFF, then that would be a count of 4. Yeah. The printing the byte should be a byte count of 1. Now, one of the interesting things, which I know is mentioned in the pre-recorded like slide videos, when it comes to this %n counter, is it rolls over, right? And so if you use %n, then it is a int star, which is 4 bytes. But if you used %hhn, then the value that's written is 1 byte. And so if you were to write 255 and then print out 1 more byte, then it rolls over to 0. It goes from 255 back down to 0, as long as you are using %hhn to write it. The act of using n does not display anything to the screen. %n only writes the number of bytes printed so far to the provided pointer. So my suggestion, and we can delve into this in a little bit here, I assume I have time, would be if you know, right? Like if I'm writing 0, and I know I've written a 0, and then for whatever reason I'm writing a 1, right, or some other number, what I would do is I would just do the math to roll it back over to 0. Right? So if my second 0 was, I don't know, 255, I would just add a space between it, because then that would suddenly become 256, which rolls over to 0. If instead of 0, I was getting, I don't know, 128, I would add 128 spaces, and that would roll that 128 on a %hhn back down to 0. Right? Like that is the naive answer. Is I may not understand why it's happening, but I definitely know how I can fix it. where the more like technically correct mastery would be, we got to figure out why this isn't doing what I think it should be doing. Okay, brief aside to finish up railroad points. So I have this E thing. This E thing is an ELF. One of the nice things you can do with this is there are methods that you can call to get information about the binary. Now, this particular binary, if I remember right, well, no, this one was PIE. The addresses and values that you get, right? So like this says arbitrary right is at 462. So like if I did E dot symbols and then arbitrary right, this is the offset into memory where this function is located. If this was not PIE, it would be the if there was no PIE, this would be the address of the function that would be consistent. But because this was compiled with PIE, this is just an offset into the binary. But we can use this to, if we get a leak, to calculate the location. And there's a similar thing for the GOT. And so you can get the address of GOT entries. In fact, let's make this not PIE so that it reflects a scenario. And so now I can go E GOT and then index into that and be like, okay, well, what is the address of the GOT entry for printf? And so because this is now without PIE, this is an absolute value, absolute address that is correct in all instances. If it was with PIE, then I would need to dynamically figure out what the address is at runtime by leveraging the offset value plus some leak. Okay, the other question in order I got was 9. Now, our handy dandy example here. I don't care. Our handy dandy example here is very similar to the scenario you have in level 9, although it may not look like it initially. And that's because having a printf call is equivalent to having an arbitrary write or an arbitrary read, right? And so if I need to repeatedly call like arbitrary write here, what could I do? I've spent the whole hour, or however long now, hour and a half, rambling about the GOT and why the GOT is a great target to overwrite. But the GOT isn't the only thing that we can overwrite to influence execution, right? To influence control flow. It isn't something that we've talked about in this class, but it's assumed knowledge from the system security class. What other things have we overwritten to influence control flow? Hopefully the person that asked about level 9 is still chilling in here with me. Somebody says return address. So that's a good target, right? Now, I don't know if you get a leak in level 9. I imagine you do. You get some type of leak. Somebody says file structs. So the modules are in order, so I wouldn't make you know anything about file structs in this module. File structs will be launched later this evening. I'm not making any changes, but I wouldn't expect you to know file structs in format strings. So the return address is a good candidate. Let's just verify here. Ruin all my good work. So we don't get a leak, right? But I still claim that the return address is something that is worth thinking about. Do you know why? How can I know where the return address is, if I don't have a stack leak? Any thoughts there? It's hard to know with Twitch delay. Right. Somebody says they know how they solved it, but they don't want to spoil it. I don't want to spoil it either. What I will say, let's grab my demo and bring it back here to temp. Export to PS1 equals. Okay. If I run my demo code here, and let's modify the demo code. Let's make it do something, because I'm done with you for now. I don't need any of this. What you essentially have in level 9 is some buff Y246, because I can't type. We have a read call from 0 into buff of some size. Maybe it's scanf. I don't really care. And then we have something like this, right? This is like the minimal example of what is going on inside of level 9. Conceptually, based on what the challenge says. And so if we compile this guy, give him a run, I could do what? %6 $LLX. Okay. What did I print? %6 $LLX. Let's disassemble main instead of breakpoint. At the other side, printf. So what's that? Main plus 86. And thank you for the raid. Who raided us? Breaksack. Thank you, Breaksack. Okay, so Twitch chat says the printf, or the format string of %6 $LLX leaked the stack, or the value at RSP. And so let's replicate that now, %6 $LLX. And what we saw right here, it prints 0, and it's getting that 0 from right here, which is what RSP points to. Where is the saved return address? Because I'm claiming that you can get to the saved return address here. The saved return address is on the stack, right? If I go info frame, we have saved rip right here. And so if we print RSP, and we take the saved rip, and we subtract saved RSP, they are hex 128 bytes apart. Well, I already know I can print, which means I could also write, right? I could change my %6 $LLX to %6 $N or HHN if I wanted, right? I could write to this location with my format string. If these are right next to each other, right, here and the saved rip, I should be able to use a format string and reference this saved return address because it's a fixed distance from RSP. If this is $6, this is $7, this is $8, this is $9, etc., etc. And so we just have to figure out, well, what is the correct index, I suppose. I don't have a good word. I think I've referred to that $ number by like 4 or 5 different terms. I don't know that there is a correct term for it. But there is some number here as we march down the stack that will get us to this saved rip. Right? If I did examine, how many would that be? Let's see if I can math. 62 giant hex at RSP. Is that right? If I don't include the space. Saved rip is E908. E908. Ooh, did I go too far? E908. I didn't go too far. Here is my saved rip at E908, and this is RSP. So I just need to do the math, or we could brute force it and figure it out. But you can do the math to figure out how many do I need to march forward to get to E908, to get to this location right here. And if we can overwrite the saved return address, then we can influence how the program behaves. So then your kind of next question, which I'm not going to answer, is what do you want to write there? Where do you want the program to jump to? Because as far as I'm aware, GDB info func win. Ah, I'm a liar. But be creative with what you want to write there. Okay, so that was what I have to say about level 9 here, where you're using a format string exploit. Oh, it does say to call win. Okay, so that's convenient. I want to say, this one says chain it into ROP. This is ROP with PIE. This is ROP PIE and input filtering. So okay, I didn't spoil it then. 9 says that there's a win function, right? And so that may be a good candidate to try and call for level 9. Now, I know one of these challenges here, there is no win function. And so you'll have to be a bit more creative with where it is you jump to and why. And the last question I got, as far as I'm aware, if I'm keeping up with... Yep. Good to have you there, man. Thanks for hanging out. Hopefully it was useful. The last question I got, which I want the person that asked to let me know if it's still an issue, is the mystery of %n. Are we going to solve the mystery of %n right now? I think I have... I think this... This is what I showed you on the Discord as an example of why we couldn't, for whatever reason in class, all of us collectively forgot how to put bytes on the stack. Right? This is just that code, so it's not like anything secret here. Because I intended of having it be a discussion point, but instead I threw it on the Discord. So if I change this, what do we have here? We have read, we have printf, and what I would need to reason about this would be 2. My secret value 2 will be my array 2, and then I need to declare that. Right. Bam. Cool. So I have this. Does that make sense? I believe it does. You're not confident, but you don't have a bug somewhere else. That's just the worst, isn't it? Okay. Let's remove all these goofy core files. Let's compile this simply. So I will say no stack protector. Because I don't want a canary, because that could change the math. I don't think I need anything else. Do not see. Check sec. Take that out. This is not what I'm working on. This is. Okay. So let's take a quick look here in GDB. Oh, let's compile that with symbols. It'll be even easier to reason about. -G gives you debug symbols if you're unaware. So we start. What I care about is give me the address of my secret value. Actually, I need to continue until the read. Cool. Go back up to frame 1, so we're inside main. Let's just make sure all of our pointers and things make sense here. If someone's curious to see it live, yeah, like let's do it live. Right? Worst case scenario, I blow up and it's all a giant mess, and we just go, all right, man, I'll post it on Discord as soon as the knowledge hits me off stream, which happens unfortunately far too often. Okay, so we'll print the my array. That gives me the string. If I print the address of my array, that is where it is in memory, and that is going to be on the stack, as we can see right here. So far, so good. That is on the stack. Somebody else here, they say they appreciate all the cybersecurity content Pwn College puts up here, but I wish there was a way to know what the topic of the stream was, like in the stream title. Yeah, it's one of the things that we're bad about. And the reason that we are bad about it is because we all share, there's many presenters throughout the week, and we all share the same Pwn College account. And so we are mods on, like, we stream to it, but we don't have the ability collectively, all of us, to change the title of the live stream. Or at least if we do, we don't know where the button is, and we're just really bad about it. I'm going to start clicking buttons here. I'm going to be like, oh, there it is. Oh, I found it. All right. Format string exploits, CSE598, Robert, and then what is today? 2024-02-02. So I can't speak for other presenters, but now that I know that it's hiding in the mod settings, I will try and update that when I start streams. The problem is that, sometimes things get hectic. They definitely get changed. I try and change them the same day that we do stream, sometime in the evening. But yeah, it's just a matter of juggling the various people when we're streaming on Twitch. So by default, it's some generic message. Okay, back to where I was. So we have the string CSE598, which is my array, which is this right here. And it is located at this memory address, which we see is on the stack. So far, so good. And as far as where are we in the program, we are inside main looking at it as if we are just before calling read. Just to kind of reason about it. Make sure all of our pointers and things are set up how we want, right? That we aren't making some other grievous error or mistake that will ruin our logic. So then if I print my secret value, we see that my secret value is a pointer, and it is pointing to this right here, which is CSE598. Right? That doesn't dereference. Okay, that does dereference. So this is a representative thing of GDB of how it's doing it. The actual value of my secret value is this right here. And then it is being helpful by showing us the string right here, CSE598. And then if I were to dereference this value, right, then I would get the first character of this string, which is C, which is hex 63. So everything there makes sense. Looks like that is set up how we would expect to then play around with it. The thing that I am particularly interested in for our format strings is the address of my secret value. And this is where I want to write. If I want to reference, this is the memory address that I need to find with a printf index to refer to this int star that will then write to this string. Hopefully that sentence was understandable. I know it was technically correct. All right, and then we'll do the same thing here with my array 2. We'll print my array 2, the address of it. That is, we see right here, right next to my array 1. So that is on the stack. And then if we print the address of my secret value 2, we see that is right next to my secret value 1. These are all on the stack. And the last thing that I'll need, where am I? I am... Okay, I am inside main. So then if I were to print RSP, or better yet, let's just do this. Let's fini, or contag, give me a backtrace. And then we select frame 0, we fini. I don't care, because right now I'm just trying to understand the layout of memory. And then to have things all nice and clean here, let's print the address of secret value and the address of secret value 2. Then the last thing that I'm interested in is RSP. These are the pieces of information that I need to math all of this out. I don't know if I did the math on any of the slide recordings. So I will attempt it live here, and we'll see if we can math this. So if I know RSP is $6, then I want to know, well, how many do I need to increment? How many past 6 do I need to go to reference these locations? And we can get that by doing some subtraction. Boom, boom. That is hex 118. Right? That is the byte distance from RSP to the location that I'm interested in. Now I need to take that number, subtract 8 because I'm already at RSP. So I don't need to include those 8 bytes. All right, so far so good. And then I want to divide that by 8. Or you could divide by 8 and subtract 1, right? It gets you to the same number here. And then let's print that off as not a hexadecimal number, but a decimal number. And I get 34. Assuming I did the math right here, accessing this memory location, which is the address where the secret value pointer is, should be 34 plus 6. And then secret value 2 we see as 1 behind there. So the printf indexes I should be interested in should be 39 and 40. Let's see if I did it right. We'll run this again. And I'm going to disassemble main. We'll set a breakpoint on the... This does call printf, doesn't it? Why does that not call printf? I'm very confused now. Temp format. Call, read, call, exit. Okay, why? Printf buff followed by 1. That should be fine. That's my... Oh, it's because I have this freaking exit right there, and the compiler removed it. Gosh dang it. Okay. Well, we will speed run that math again. The question is, why subtract 8? Well, since I'm going to have to do the math again, we will see. Do.c, gdb, a.out. Let's make sure we actually have a program that calls printf. My gosh, we do. Okay. So let's continue, or let's run it. Let's get to the other side of read. I don't really care right now. And we'll print off the same values. The math should be the same since I compiled it the same way, but it doesn't hurt to double check, right? Let's not have a major screw up because I assumed something. Where am I? Oh, I didn't compile it with... Okay. Run. Hey, I don't care. Address of my value. Address of my value 2. RSP. So if I were to look at... And then let's get the... Yeah, we'll do the hexadecimal distance from my value 2 to the stack pointer, big one minus little one. I got hex 110. And so if I did examine, what is that? 222 giant hex at RSP. Did I go in the wrong direction? No. Right here is RSP. And this is $6. So then this is 8, 10, 12, 14, 16, 18, 20. Where am I trying to go? 8F0. So 22, 24, 26. Did I do that right? 26. Because RSP is 6. It's be 7. So then 8, 10, 12, 14, 16, 18, 20, 22. I didn't do that right. 24. 24 is the correct number. Looking at this spatially. Do you agree, Twitch? Like if we just print this out and we count it, it should be 26. You think it's 23? To go from 7E0, which we know this is 6, then you'd be 7, then you'd be 8, 10, 12, 14, 16, 18, 20, 22, 24, no, it is 26. I'm mixing up my pointers here, but if I'm trying to get to my secret, where am I trying to get to? 8, 8. Did I not go far enough? Where is this? E8, F8. I didn't go. Gosh dang it. You're saying this right here. 8 is even further away. Value 1, value 2, RSP. Okay. Where is F0? Did I still not dump out enough? 8F0. 8. Okay. I just can't count. So, we agree this is the stack pointer, which would be $6. Then we have 8, 10, 12, 14, 16, 18, 20, 22, 24. This was 24, 26, 28, 30, 32, 34, 36, 38, 39. So it's 39 and 40. Right? Because the addresses that I'm trying to get to access the pointers are 8F0 and then 8F8. Now, that's the same number I came to when I did the math. So I feel pretty good about those numbers now. Things like make sense. It's a good sign when you get the same number using two different techniques, right? Now the math, the reason I need to subtract 1 is because if I start at this address, I'm already including it when I say I'm going to write to 6, right? $6 is this. But when I'm counting, or when I compute the distance, I'm including these 8 bytes. But these 8 bytes are already included if I start counting from 6. And that's why I subtract 8 bytes, or 1 from the difference after dividing by 8. Because what you're finding here is how many increments of 8 bytes are they apart from each other. That's why when I'm going down here and I say 6, 8, well, that's because these 8 bytes I know are referred to by $6. These 8 bytes will be referred to by $7. These 8 bytes will be referred to by $8. And we could go one at a time, right? But my mouse left click button isn't that good, and it's going to eventually disconnect here, and it becomes a pain to count, right? Especially when this distance grows quite large. So the way to kind of mathematically say, all right, well, where is this, right? Without having to visually look at it. Although visually looking at it is definitely helpful. The way to do the math is you grab the big one, you subtract the little one. That gives me the byte distance of hex 110. But what I'm interested in is how many 8-byte increments are there? And it's hex 22. And then because I know this right here already includes $6, we subtract 1. And that gets me to 33. And we add 6, that gives me 39. And then this was to F0. So F0 is $39. This one is right after it. It's E8F8. So it's going to be 40. Like if the math doesn't work for you, like you're like, hey, this doesn't make sense, totally fine, right? You can do this and just dump out a whole bunch of stack memory and count it yourself. Or you can use like a for loop in Python and just print it out, right? It's not that hard to write a few lines of Python and say, print me $1, print me $2, $3, right? Until you find something that looks like what you need, right? That's perfectly fine if you're trying to just kind of get your head around the concept. But this I find to be the fastest way at a conceptual level to figure out what index do I need. Okay, so that was a lengthy rant to get to the numbers 39 and 40. So now, I am here at the read before printf. And let's disassemble main. I have no breakpoint. Let's set a breakpoint at main plus 115. So I'm going to be just on the other side of this printf call. And while we're at it, let's also print, what did I call them? My array. Print my, I'm not in the frame. Frame 0, frame 1. Print my array, and then my array 2. Okay, so they are right now this string value. And we're going to overwrite these with this format string. If I say percent, what were my numbers? 39. Let's have a space here. Am I actually in? Where am I? Continue. All right. I am inside the read that will set this buffer. I am right here. I'm going to go 1, 2, 3, percent 39 $n, percent 40 $n. That feels good. All right. Okay. We did it. We segfaulted. That is a shame. Why did we segfault? Printf positional. Where are you trying to write? All that talk. What did you get? That is 3839. That is literally the numbers. 8, 9, 5. Eight, 9, 5, something. Where the heck did it get that from? All right, let's try this. Percent $39 sign P. Okay, we're on the other side. What did we print out? This. And then let's print that as a string. $39 sign. I just recognize the ASCII characters. 39 should be good. Let me think. Did all the fancy math and then it says no. Finny. Examine 20 giant hacks. I need like, what was it, 50 giant hacks at RSP? Alright, there's my A's. Here. This is what I'm printing. So I'm either off by 1 or I'm off by 2. So that means 41 should get me what I want for sure. We run it. Percent 41 $sign P. Okay. And what did it print? 8E9. 8E9. Okay. Why? Because that would be the distance here is... Did I get myself with the subtract 1? Then it's 40, 41, 6, 7. Yeah, I did. I got myself with the subtract 1. It's 40, 41. Gosh dang it. Okay. 1, 2, 3. Percent 40 $sign N. Percent 41 $sign N. Hey, you know, it's bound to happen. Okay, we didn't seg fault. We reached the break point. Now, if I print my array, it's going to be some gobbledygook. And I should be able to cast this as an int. Right, because I did n should be 4 bytes. The giant X there. Okay, there we go. When I was printing it, arrays are actually pointers, and so this was not doing what I wanted. Where if I use examine, then it'll dereference the pointer because arrays are really pointers under the hood. And if we examine the giant hex of my array 2, we see that both of these, and what I care about is the 4 bytes. You asked because you remember that your solution. No, I'm totally capable of being wrong, right? One of the things that like I preach to everyone on stream is like work from first principles and like prove out what you say. It's one of the reasons why I like to be somewhat prepared for live demos because like my total philosophy on like exploiting things is I work from first principles and like what I think is right because I'm never going to remember every piece of knowledge that I need to pull something off. And that's why I'm totally cool doing it live because then we all get to see what's wrong. Okay, and remember that since I used up here %n, that is going to be writing an int, so it's 4 bytes. Right. So somebody else here in Twitch says countless hours I've wasted because my assumptions about simple things. Right. It was a super simple thing. I was even looking at it here visually and counting, and I probably counted to 40. But for some reason in my head, I was like, "Oh yeah, but we need to subtract one." When I literally just visually showed you that you didn't need to do that. Right. And that's where. What did I do when I was like, oh, wait, this is wrong? I went back and used my understanding of how this works to re-verify what I had assumed. And so I was wrong, but I didn't lose too much time being wrong because I was immediately ready to be like, okay, we need to double check something. And that is probably the best thing that you could do. Don't assume that you are right, right? Assume that you are wrong. The computer is usually right. So what we saw here is I get the same integer written to both locations. It's 3 and 3. Only because I'm pretty, I appreciate that. All right. And so when I did my %n%n, we see that it's the same value being written. But you'll also notice that in my format string I did here, I did not put any space. I did not use any fancy padding symbols. I put this right next to this. And so how many bytes were printed to the screen before this first one? It was just the characters 1, 2, and 3. And how many bytes were printed to the screen before this second one? Well, it's still 3. It's just those same 3 characters, 1, 2, and 3. So in both of these instances, it writes the integer 3. And since an integer is 4 bytes, that's why we see the lower half of what was CSE598. Right? This right here is my 9. This right here is my 8. This is a terminating null byte of that string. Because when you print out a string as hex, like in this format, you read it from right to left. And so we overwrote the first 4 bytes with that integer value of 3 and 3. And so we see that it doesn't change. Now, if I were to do that same thing here, and do percent, or I don't know, 1, 2, 3, 4, 5, %40 $n space %40 $n, or 41. No, $41 n. Right? This is different. And if we look at my array and my array 2, we see 6 and 7. Why do I get 6 and 7? Well, let's go back up to my format string. I did 1, 2, 3, 4, 5 space. So at the time of this being evaluated, 6 bytes have been printed to the screen. And that is why I get 6 right here. Then I have this space right here. And this is a space that is output to the screen. And so the number of bytes that have been displayed to the screen from this section here in yellow, the count is at 6, which means this second %n will result in writing the integer value 7, because it's 1, 2, 3, 4, 5, 6, and then 6 for this space, and then 7 for the second space. And that's why we see the values down here of 6 and 7. And then the last thing I'll show using this is, what if I did, and this is textbook How do I do the amazing blank space padding thing? What's the magic character? You guys know because you're doing it. Where I have to refer to the old man pages because I am not knee deep in printf at the moment. What's the other symbol that I need? Print argument. Were you align? Is it asterisk? So then what is that? What does that whole bad boy look like? Whatever. I won't do that. We will advance. Oh, I'd have to change my binary anyways, wouldn't I? Somebody hit me. Percent padding C. That'll work. Okay. So let's disassemble main. Like I would find it and we could do it, but I don't think you want me to spend 5 minutes poking around a man page. So I'll trust you there. We'll break at main plus 115. We'll run this. Okay. Percent. Let's do 255 C. So that's my padding. Percent 40 $HHN space 123 percent 41 $HHN. So, assuming you guys didn't trick me here on this padding, we're going to output 255 padding bytes for a character. And we'll hit it and see, right? Like, it's okay to not know, okay? Run it and find out. That is how people figured this stuff out. But what I would expect, based on what you're telling me, is we're going to write the first value here. Should be 255. Then I have a space, which would make this 256. But since I'm using HHN, I'm only writing a single byte. So 255 rolls over to 256, which would be 0, if I'm mathing right. At which point, this becomes 1, 2, 3. And so I should have the values, if I'm thinking about this correctly, 255 and then 3. See if I'm right. I could be off by 1, right? Maybe I didn't get the padding right, and it's going to be like horrendously off. Okay, well, there's my 3, so that's a good sign. And there's my FF. There's my 255. But I didn't get all these zeros, right? Well, what happened? Well, remember, I prefixed my N with HH. And H% N will write the number in 4 bytes. We'll write a 4-byte number. Percent HN will write a 2-byte number. And percent N will write a 1-byte number. And so I wrote a 1-byte number that was 255, which is hex FF. And then when I did this, it rolled over. And so then it became 255, 0, 1, 2, 3. And I wrote 3. And that is what we see in the single byte that is pointed to. FF and 3, which if we print as a decimal, XFF, that's 255. And if we print as a decimal, OXO3, that is 3. For the person that was asking about percent N and how that kind of works, Was this a reasonable enough demo and explanation to kind of get your brain juices going? They said, yep, they were doing HNN, not HHN. That'll do it. That will do it. And hopefully, this was good to see how you can use GDB to kind of verify what you think is going on, right? Like, now that we are no longer in microarchitecture exploitation, GDB is here to help, right? And we should be happy that GDB is here to stay for at least the first half of the semester. Does anyone have any other questions? I think, longest office hours for the semester right now, but that's okay. I don't think this is a particularly hard module, like from a concept standpoint, but it does require, when you do make a mistake, it can be a little bit hard to pin down why something is happening. And so hopefully, me making some mistakes on math, me making some mistakes here and there, and kind of going back and being like, okay, well, how do we figure this out, is helpful so that you can use a similar process to reason about what you're looking at. Give it a moment for the Twitch delay, and if nothing comes out, I'm going to call it on the stream. Twitch chat says, I agree, the troubleshooting part is the best part. That is the live experience, right? Things break, they don't go according to plan, and hopefully we manage to recover, right? Way better than just a canned, this is what I'm going to show you, and it's always going to work correctly every time. Right? It blows up for me too. I forget how things work. I read the man pages, right? Where is this asterisk? I can't say the word. I know it's in here. Oh, I didn't escape it. There we go. Precision. An optional precision value may be used by using star. I didn't guess precision for a keyword there. All right. Anyways, I appreciate everyone hanging out. I'm going to end the stream here. If you do have questions, please ask on the Discord. Even if I'm not logged on, I do periodically just pop open on my phone and see if there's any questions for 598 to try and answer. So even if I'm not live on the Discord, I will try and answer or check in periodically. With that, I'll leave you guys. Goodbye and good luck.